We're going to continue now talking about the idea of regression and curve fitting in general, as it were, as well as thinking about regularization. These are key concepts in data science, model building, neural networks across the board. So I'm trying to give a set of examples that are very simple and intuitive for understanding how these things work. In the last lecture, I talked about AX equal to B in over and under determined cases. It is critical that you understand how regularization works in that case, because that is the simplest scenario possible. And now we're going to start building upon that and start understanding a little bit more about what the possibilities are and the solution types we can achieve in thinking about this regression framework. Again, this is out of this book, Data-Driven Science and Engineering, Brunton and Kutz. You can find more information here at databookudub.com. All code, all lectures, notes, everything is there. Okay, so you go check it out, and this is from section 4.4 out of the book. So let's get to it. I want to do thinking about, again, as optimization. It's all going to come down to some optimization. And optimization is really the cornerstone of all of the regression. Right? The idea behind the regression, again, is that you're going to impose a model with some parameters, and you're going to try to map an input to an output. That's it. So that's going to require to do an optimization. All of data science, all of machine learning can be thought about as optimization on data. Okay? So optimization essentially is synonymous with machine learning and deep learning and AI. All of it's optimization. And so you just want to think about that a little bit. And it starts all here with regression. Regression is just simply, you give me a model, find the parameters that work for that data. Okay? And these models can be quite complex. But we're going to start with very simple models and work our way up. I'm going to emphasize this again, and I showed this in the last lecture. Regularization is critical. In fact, I would say that's where all the magic or all the interesting happens, is in the regularization. Normally in an objective function is what you're trying to do in an optimization. You're trying to minimize some objective function. But then often you apply a regularizer, and the regularizers are what determine the types of solutions you're going to get out. And of course, what you're really trying to do is engineer for yourself a solution that is meaningful, interpretable, potentially parsimonious, so you can really have a nice representation of what's going on in your system. So regularization, really an important concept. And I'm going to show you how diverse the set of solutions you can get are by just applying different regularizations. Okay? So here is the simplest example possible, I think, or one of the simplest example possibles, which is I'm going to take data generated from this here. So I'm going to say my model is simple parabola. F of x is equal to x squared, plus I add a little bit of noise on it. And I'm going to show you some example of this. It's not going to be very much noise. You're going to clearly see that it's a parabola. So I'm going to take some data points, and I'm going to put a little noise on it. It's still going to look like a parabola. Okay? But what you're going to see is when I go solve this problem, how do I do it? What are the consequences? What do regularizations imply? Okay? Now it's easy enough for me to write down this model ahead of time and say f of x is equal to x squared, so I know what the truth model is. However, in general, when you come to a problem with data, you do not know what the model is. You don't know that it's a simple parabola underneath there. And oftentimes you can't just with your naked eye tell what it is. So the idea is to start thinking about what are the kind of architectures and methods that are going to reveal this kind of structure to us through the regularization. In fact, the regularization is going to tell us a lot of information about what's really the underlying model that you need to be using. Okay, so here is what we're going to do. We're going to do 100 realizations of data. We're going to build a model here, y equals f of x beta. So I have some inputs and outputs. So what I'm mapping is my data points to some output. So remember, I have f of x is equal to x squared. Now I don't know this. I just have measurements. So I have to impose a model that's going to map my measurements to an output, and I have to find the beta values. So I don't even know that it's a second degree polynomial. So for instance, I might look at data and say, well, what's to say that's not a line or a quadratic or a cubic. So what I'm going to do here is more specifically look at a pth degree polynomial. This is represented here. So that the beta terms are the loadings or the coefficients of the linear term, the constant term, the linear term, the quadratic term, and so forth. So these are the weights given to these here, or again the loadings, to try to predict an outcome, which is in fact the XY plot that I just, we talk about, which is the parabola. Like I give you X values, can you predict the Y values? Okay? So it's a very simple model, but I'm going to have a little bit of noise on it, and you don't even know what the model is. So that's important, even though obviously it's going to look like a parabola. In most data science problems, you don't know what the right model is to use, and so you're going to have to guess a model and then start figuring out, can you in fact refine it to get you the right type of model or the best model possible. Okay, so that's a generic architecture that we're going to use. So let's go to some code, and we're going to run through this in a simple example. All right, so here's what we're starting off with, the parabola. Okay, so it's going to have 100 points. It's going to be on a domain of 4, so it's just f of x is equal to x squared. And here you go. Build a linear space from 0 to L, f of x is equal to x squared. Parabola with 100 points. Very simple. Now what I told you is, though, that's how I'm generating the data. Now, as a data scientist, I don't know this. I just collect the data, and my job is to figure out what is a good model to be using in the first place. Now, obviously, knowing the answer is helpful, at least for understanding, but in general, this is what you're going to have to do, is you don't know the answer is, so you're going to figure it out. So here's what we're going to do. We're going to build a library. Here it is. The library is what I just showed you. We're going to fit up to a 20th degree polynomial. We're going to say m equals 20 for j equals 1 to m, and what I do is build these polynomial libraries. So in other words, I can say, okay, I have the constant, I have x squared, x cubed, all the way up to x to the 19. So those are the possibilities of terms I might use to fit the data. So a 20th degree model. Now, I don't necessarily know any better. I wouldn't necessarily have any information that would tell me what the right model is. So I'm just going to make this up, and then I'm going to start saying, okay, so what I want to do with this is now try to figure out if there's a good model to be using, and how would I get it. So what I'm going to show you here is that what we're going to do is we're going to actually take 4 examples of this here. So I'm going to do a loop right here. It's going to go 4 times. It's going to take that parabola and add a little bit of noise to it. 0.1 rand n. And what I'm going to do is I'm going to show you what these 4 models look like. Okay? And I'm also going to do least square fit on these. And so you can say, if I do a least square fit, you're going to say, with this 20 degree polynomial, how well does it fit the data? So let me just show you what running this gives me. And I made a little chart. Here it is. So this is what I get out of this. So here's my parabola, okay? And the purpose of showing you what you're seeing here is these are 4 runs with just a little bit of noise. So the noise on here is very tiny, actually, so you don't even hardly see it. In fact, I don't think I plotted the noisy runs on here, but if I had, it'd clearly look like a parabola. It'd be just basically floating near this line. The point is this. I added a little bit of noise, and I want to show you if I just simply do something like backslash, which does a least square fit, here are 4 different solutions with 4 realizations of noise. Notice how different they are. Particular, look at the loadings here. So this is the constant term, the linear term, quadratic, cubic, and so forth. But here are the distributions. This solution below, the quadratic term is different sign, and the cubic are flipped. It has this very big component, which is an x to, I think, the 16th, which this has a big x to 16th here. Whereas over here, all these structures with just a little bit of noise change gives you fundamentally very different solutions. Okay? And by the way, these really matter out here, especially the x to the 15th and x to the 16th. They have really big impact on the solution that you're going to get out of this. Okay? So all this is trying to tell you is a little bit of noise, or just even a different random draw, can give you very different models under this regression where I was trying to fit a 20th degree polynomial. Now, of course, when you look at this, you wouldn't say necessarily I should fit a 20th degree polynomial. But remember, this is a very simple example where you know the answer. In a lot of data science contexts, you don't have the ability to visualize data so clearly that you can say, oh, I should just fit a parabola to this. Oftentimes, you don't have that information that you need to make those decisions, and you can get results like this, which are highly dependent upon the noise that was actually in the sample. And so what you don't want to do is generate a model that is so noise dependent or so subject to noise fluctuations. So what we're going to do is we're actually going to say, okay, let's come back here. And let's come to here, and let's start framing this back to here. So notice what this actually is. It's a regression to, let's say, a 20th degree polynomial. And so when I regress to this 20th degree polynomial, this is just ax equal to b. It's exactly what we considered in the last lecture. My regression boils down to ax equal to b. And I already showed you in the last lecture that the regularization you impose on ax equal to b makes a huge difference on the solution types you're going to get out of this thing. Okay? So that's the one thing I want to think about is what's that going to mean for this problem. So what I'm going to walk you through is 6 different ways to solve ax equal to b in MATLAB. So I think we can all agree there's my ax equal to b. I build a matrix A. There's the b over there. This is the input-output map. All I got to do is determine those betas. So I'm going to show you what happens in MATLAB when I do this. And I'm going to show you all these built-in ax equal to b solvers. Okay. Different regressions. So this is what this part of this code is called. And for instance here, I'm going to do one thing first is I'm going to do some different regressions. I'm going to pick lambda is going to be parameter 0.1. The lambda is going to be used in these sparsity promoting algorithms that are built into MATLAB, including the lasso command. So you want to say how much L1 penalty do you want? That's determined from here. Okay, so let's build this thing. And now what I'm going to do, I'm going to set this up. Oops. There we go. I'm going to set this up in a loop. I'm going to go through the loop 100 times. Here it is. So what I'm going to do is make 100 different noise realizations of this function. So every time I go through here, right, I have a little bit different noise. Okay? So essentially what I'm getting is 100 trials of this data, with each one with different noise characteristics, which is Gaussian distributed, so very simple. The noise is fairly small. And then I'm going to say, okay, let's fit the data with a model. And here's what we're going to do with this. In fact, what I'm going to do each time is I'm going to find the loadings. In other words, remember, when I fit this, I get a set of parameters beta. Those are the loadings. Those tell me how much the constant's important, the linear term's important, the quadratic is important, all those terms. So when I do my regression, I find values of those. And I'm going to find those values for each noise realization. And then what I'm going to look at is over 100 realizations, what is the statistics of the loadings? I really want to know how much are they changing every time I change that noise a little bit. Okay? So I have parabola data, I do the fit. Here's the first fit I do. Pseudo-inverse. Okay? So this is going to be essentially a least square regression. And so what's going to do, it's going to give me some kind of L2 minimal norm. Okay? The second one, that's called A1. That's the first AX equal to be solved. A2 is the second AX equal to be solved. And that's the backslash. You're going to find an interesting thing here. The backslash gives you an interesting structure itself. And you can ask the question, what is backslash actually doing? And it turns out it's doing something with a QR decomposition. but we'll see what the results look like. And by the way, for each one of these, I compute the error. So I compute how well it did, and then I have the values of A2, which are the loadings, and so I can also see how the loadings are changing on each single run. I can also do lasso. Here's the lasso, and in fact, the lasso I'm going to do lambda 0.1, and then there's another parameter alpha which parameterizes the lasso, which is 0.8. So I'm going to do the lasso twice. One of them promotes more sparsity than the other, I believe. Okay. Then I also do, that's solution 3 and 4. Solution 5 is the command called robust fit. This is, again, another AX equal B solver. Did you know there was all these AX equal B solvers? So you have pseudo-inverse, backslash, lasso, robust fit, and also ridge. So these are 6 different architectures, or it's really 5, with lasso being 2 different instantiations. So I give you, 5 or 6 different AX equal to B solvers, and you ask the question, which one should you use? And in this model here, which is just trying to fit a parabola, we're going to see some very interesting features pop out of this. This is why I like this example so much. It's so simple that when you understand it, you can start to understand what you're trying to do in the regression a lot more cleanly. Okay, so I'm going to run this and show you the results of this. All right. Let's start here. Okay, so first of all, let me go back and show you this. This now is the data. What you're seeing here is 100 trials of the parabolic fit. So remember, the parabola was at perfect fit. Now what I've got is 100 of the trials. And by the way, this is if you do the pseudo-inverse for 4 of those random of the 100 trials. So you see the parameter loadings are quite different in these. Okay? But here, notice I haven't added that much noise, right? This looks like a parabola. So it's very clean. So what the idea would be is like, you know the answer. This should be a parabola. The data looks like a parabola because, in fact, I haven't even added that much noise to it. And then the question is, how well do these different models, how do they handle this? What do they try to do to predict what's going on in this system itself? So I'm going to show you this in a statistical framework. This here figure, I think, speak volumes to what we want to do. It tells you a lot about the structure, and it tells you a lot about regression. What I'm showing you is 6 panels. What I'm showing you here is the pseudo-inverse, backslash, lasso 1, lasso 2, robust fit, and what was the other one? Ridge. Okay? So what you're seeing here is 6 different AX equals B solvers that are built into MATLAB. All of them have, the only difference between all of them is the regularization. And you can see they produce very different results. Now let me tell you what these are producing. What you're seeing on the x-axis is, this is the, so what you're seeing here is 1, 2, 3, 4. This is the values of the constant term, the linear term, the quadratic term, the cubic term. So in other words, this is the polynomial order, and this is the variability over those 100 trials. So I've done it in a box plot, which shows you the variability that you get trial by trial over the 100 trials. So notice what you're getting here. When you do a least square fit, look at the massive variability you get. See these big error bars? They're all over the place. In fact, they all look like they're centered around mean close to 0, but they have very big variability. So every time you do this regression with a least square fit, it gives you very different results. And it just uses all the coefficients But then as soon as you change the noise a little bit, you get a very different result. In fact, what you don't want to see in a model is this kind of variability. So the uncertainty in this model is extremely high. Okay? And not only that, what's problematic here is look at the terms that are very high degrees. So x to the 16th and 17th. These terms are highly volatile, and so you get a loading that changes. If you try to do any kind of, let's say, an extrapolation with this, you'll be destroyed with this kind of model. Okay? The pseudo-inverse, the backslash does something interesting, which is, notice there's several of the values that are turned to 0. And then it has some variability on the others. Still quite high variability, but this is a QR-based algorithm, and it actually does set quite a few of the coefficients to 0. And I'm not going to talk about the structure of that QR algorithm, but there it is in terms of what you get. So notice, very different solution types, very different answers. The only difference is the regularization procedure. Okay, remember, this is all Ax equal to B. And in fact, in a moment, I'm going to show you the error that despite the variability in all of these, they all produce they all produce great error, right? So the error is almost the same for all of them. It's just that how they do it is very different. Here's lasso. Here's lasso again. So here's lasso. Notice this is an interesting solution because it does give you a little bit of linear. Look how it pops up that quadratic term right here. So the quadratic term is quite high. So in fact, lasso is very nice because what lasso is trying to do is promote sparsity. So what it's going to actually do is say, well, you know what? How many of these terms could I set to 0? And it figures out that, like, hey, this quadratic term seems to work really well. I will keep that one. And I'll try to set the others to 0. Now, there are a lot of benefits to doing this because now all these model terms have dropped out. So your model becomes parsimonious and very interpretable. Okay? This isn't always what you want in a model. However, in this case here, it actually is highlighting you very nicely that this thing should be, in fact, a parabolic fit. So if you didn't know that ahead of time, this is giving you a lot of clues to that. Now, if I change a little bit of the weightings of these parameters, notice what happens here. It picks up the linear term, and it drops the quadratic term. So it tries to actually say, well, the linear term, in fact, a linear line, the parabola I showed you, a line does a pretty good fit. So it actually starts using the line and a little bit less the parabola for that fit. Robust fit, here's what you get here. It's again, it's this one here basically tries to throw out outliers, but there's not many outliers here, and so it ends up just doing basically something very similar to the QR up there. And then finally, Ridge does a dual penalization, has a little bit of L2, L1 penalty in it both. And so you can see what it's doing here. It does something very similar to what the lasso does. Picks up a strong linear term, quadratic, a little bit of cubic, but it does try to zero out terms. So there's great diversity of solution types. Now this is really important. Remember, when you go to a real problem, you're actually trying to figure out what is a good model as well as the good parameterizations. So this is giving you a lot of information about the regularization can really help you find better models. That's, I think, one of the take-homes from here. And also that regularization has a massive impact on what solutions you're going to get out of this thing. Remember, all of these have the same objective function, but all of them have a different regularization. And I want to show you the results of this here. Let me kill this. This is an important result here, which it's going to show you in this box plot here. What I'm showing you here is the error versus the model. Remember, I did 6 models. This is my pseudo-inverse, backslash, lasso, lasso, robust fit, and here is the ridge. Notice on this scale here, it's pretty small. They're all very small error. So the error is all small. In fact, most of the errors are comparable, so you could say, like, there's no difference in how it's handling the objective function. So the objective function, which is, say, solve for me this ax equal to b problem, give me the best, lowest error, they're almost equivalent. But how they do it is extremely different. And I just showed you that plot. So the objective function seems to be sort of stable. They all do the same thing. They all have pretty equal performance. But then how you regularize can give you very different information. And so I think you always want to think about that a little bit. In the problem you're going to try to solve, what are the regularizations you want to bring to the table to really get that thing nailed down? Okay, what I'm going to show you in this last two plots here, I did one other experiment there that is fairly simple. He said, well, I picked a 20th degree polynomial just randomly and just did this experiment. But you could ask, well, what happens as I change the degree of the polynomial? And now you're going to say, so for instance, what if I just said I fit it to a constant? I take the data, fit it to a constant, or a line, or a quadratic, or a cubic, and so forth. So what I'm showing you here is fitting up to degree 10 polynomials. So this is the error versus the degree of polynomial I pick. So if I just pick a constant, check, this is my error. It's pretty high. So in other words, a constant does not fit that parabola very well. I think we all agree on that. If you just naked eye put a line through it and say that's my constant, you would get a high error. Okay, let's make it a line. So if I make it a line, look at my error drop down to here. So my error really drops quite significantly, right? Now it's a line fit. How about if I add constant line plus parabola, I drop it to here. And notice, as I add more terms, third degree, fourth degree, fifth degree, cubic, quintic, quartic, quintic, so forth, notice that my error doesn't really improve. So in other words, this is going to be an important concept as well, which is this idea of parsimony and a Pareto front, which we will talk more about in the next set of lectures, which is I now have the ability to generate different models. And notice that as I generate these models, what I'd really like to do, if I see a curve like this, I should probably just say, well, look, I can do really well here, and I'm not gaining anything by adding higher degree polynomials. In fact, if I zoom in on this region here, that's what this plot is, notice that my error on a zoomed in plot is doing worse the higher degree polynomial I pick. Which is usually a little counterintuitive, because normally what you think is, well, the more flexibility I give my model, the more parameters, I should be able to just keep dropping my error down. And this says, actually, you're starting to do worse by adding more parameters, because in fact, this thing really wants to be a quadratic. So this idea of interpretability coming through your regularization is really critical. And notice it's all being done in the regularization. Everything I talked about here was just ax equal to b, right? And so that's the one thing you want to start thinking about a little bit, is that when you're doing regression and you think about the regression and the objective function and the regularization is, I think, where you should be spending a lot of your time thinking about, because that's going to give you critical information about the structure of the solution and its interpretability. Okay? More can be found here, databook.com, uw.com, along with the notes, all the code that was just run, Python, as well as MATLAB, more lectures on a broader range of topics in data science as well. And the next lecture up, we're going to start talking a little bit more about Pareto fronts and optimal model selection.